Yes, coming back to our discussion on sandwich panels. So what we have seen lastly is that we were able to get an expression for the equivalent flexural modulus for the resulting sandwich structure, which is this equation which we have written in terms of the volume fraction of the face material, that is F, the modulus of the face material EF, the modulus of the core material EC, constants B1, B2 or C1, C2 as we have been calling them, which are loading dependent, and D by L ratio, which is the depth to the length ratio of the beam, square of that, and the GC value, that is the shear modulus of the core material of the sandwich that we are referring to. Now, what we were looking at was that comparing the sandwich structures or sandwich panels that we are able to generate by combining two different type of materials, one being the face sheet and second is the core here, and then how they are more efficient than the materials of the face and the material of the core itself. So what we observe here is that it's a plot between the flexural modulus E and the density of the sandwich structure that we are able to generate with different values of volume fraction, different F values that you observe here, represented by these green dots. And along with that, we have plotted this for a given value of, for a fixed value of B1 by B2 or C1 by C2 as 3, that is for a particular value of the loading configuration, and a fixed D by L value of 0.04. For that we are able to plot it, and what we are able to observe here is that the resulting materials, that is, this is the core material, here I have the face material, but the resulting sandwich panels, various types of sandwich panels that we are able to generate by combining them in different ratios of C and T are available here. They are this curve, we are traversing this curve, and what you observe here is that we have plotted various selection lines onto it. I'll look into that in more details in our own Excel sheet that I'll just show you here. So what we observe here is that this is an Excel sheet which is available with us, in which we are able to plot this expression, that is our value of the flexural modulus of the equivalent flexural modulus of the sandwich structure that we are plotting in terms of its F value, and B1, B2, and the material properties of the face and the core. We have written here the Excel code for this, in which we understand that we are just giving the values of the E value for the core is taken as 0.25 gigapascals, and for so what we observe is that we have the core value for E value for the core is 0.25, E value for the face is 46 gigapascals. Density of the core I have taken as 200 kilogram per meter cube, and the density of the face material is taken as 1570. Accordingly, taking a Poisson's ratio of around 0.29, we have got the G core value of around 0.10039, and EC by EF ratio is taken as 0.00554. Accordingly, we have plotted it for various values of volume fraction. F is equal to 2T upon D, and these values are, the density value has been calculated. Now that we have calculated the density of the sandwich structures based upon our expression that we derived based upon the simple rule of mixtures, which is giving us the value of density. So we have density of the sandwich here given as 204, 206, and going up to around 1570 for total. This is one, I've just taken it. One is actually when we have only the face material, that is volume fraction of the face material is 1, in 100% face, that is 1570. And then we have calculated the equivalent flexural modulus value based upon this expression that you observe here. So these values of equivalent flexural modulus that you observe here 0.40, 0.65, they are plotted here, and this is what we observe here that we are plotting here. So what we have plotted here is that these red dots are actually representing the base material. The red dot, this one is for your face, this one is for your core, and these are the blue curve here is actually representing the resulting E flexural value or the equivalent flexural modulus for the sandwich structures for various values of volume fraction of the face material. So what we see here in this chart now, that the same thing I have now brought it into my presentation. So what I observe is that this red dot, as I said, is representing the face material here, which is nothing but a CFRP, that is epoxy carbon fiber. And then this one is the core material, which is nothing but polymethyl methylacrylate high performance core. So we have these two materials given here, and the blue curve here is actually representing the properties, or exactly the property, actually the flexural modulus or the equivalent flexural modulus for sandwich structures that are generated for varying values of F, that is face volume fraction. It is 0.003 up to going up to 0.9, and obviously then we can go up to 1 also, but and actually 1 doesn't matter because 1 will be just the face monolithic material only. So this is the actual output of that, and we have plotted flexural modulus E on a log scale versus density of the resulting materials on a log scale. What I observe here is that when I plot the material index, that is third root E by rho, which is the material selection index for selecting materials for panels. If you recall our discussion earlier in the class, it is the material index for selecting materials for panels, and accordingly the best materials are available to us this way, in this direction. And the observation is very clear that the two materials, the input ingredients of the sandwich are this red and this one, and the sandwich structures that you generate for various volume fractions of the face material, they are traversing this path. Obviously, if I want to maximize this third root E by rho material index, we observe that this maxima is we observe that this maxima is reached here somewhere, where you find that this value is giving you, that is around F is equal to 0.04. So when F value, the volume fraction of the face, is 0.04, at that point you find that you achieve the highest value of the material index third root E by rho. Means but obviously this value, this is for given value of the constants B1, B2 or C1, C2, depending upon the geometrical conditions of the beam. So what we can take home from here is very simply that what we can simply take home from here is that the sandwich materials that you generate here, they are better than the individual constituents taken separately, and in terms of material index they perform much better than this. And obviously you can do the optimization based upon whether it is a cantilever beam, whether it is a simply supported beam, or any other type of a beam. So this takes me through our discussion on sandwich structures. So we have completed our discussion on composite materials as a type of hybrid material, and the second hybrid material which we completed today is about sandwich structures.